Good morning, all of you. And this is the sixth lecture on image processing. And overall, I think this is the eighth lecture. In the last class, we were discussing about histogram equalization, right? Do you have any questions on that before I move on to another variant of that where you do this histogram thing in a locally? So do you guys have any questions? Is that clear to each and everyone? Okay. If so, let me move on to another version of this histogram equalization, where you would be applying it locally, not throughout the image. The reasons for this are very clear because you want to enhance the details for a small portion of your image. So maybe your whole image has all distributions, but you want to locally enhance certain things. So that's where this local histogram equalization could be useful. Okay. Now, assume that you are given an image. Okay. Uh, and for the time being, ignore about the pixels that are there near boundaries. You ignore them. Now, what do you think? How can you apply this local histogram equalization? What are your thoughts about that? What What do you think could be the way you apply? Don't worry about this border pixels for a moment. They will always be a special case. Okay, so you would see how you do it later on. We'll come to that. Let's say I want to work about this pixel histogram equalization. How do you think locally you could apply it? Any idea about that?
Sir, while making use of neighborhood of that like 3 by 3 neighbors.
Correct, correct. It could be 3 by 3 is typically small, extremely small for histogram equalization. It is good for applying a filter, but not the histogram equalization. You will go for a bigger windows. For example, you might be using some 20 by 25 by 25 window around centered at that pixel. Okay, this I haven't drawn a bigger image, but assume that I have much bigger image and overall of course I would typically consider a symmetric one, not the way I plotted it there. You take that, then you find out the histogram for all the pixels that are, let's say I have a 100 by or 100 by 100 image, then I could say consider 20 by 20 window around each pixel. And how many total pixels are there here? 400 pixels are there. For these 400 pixels, you compute the histogram, and for that you apply histogram equalization and now replace those pixels there. So it is like a sliding window. So you have a bigger image, you take centering that particular. So by the way, what is it that you are going to replace? Is it that you would replace you got from here? So what do you think now? I have an histogram is there. Okay. An equalized histogram, I got it. Then what will you do? Can you continue the story from there? I took around a pixel centered, I considered a window there. Okay. Then I obtained its histogram. I did histogram equalization. I got the other window. Then what will you do? So for a pixel, you have taken centered in that pixel, you have taken, let's say, a 20 by 20 window. Okay. You got one histogram. And that whatever we did yesterday, you have done all those things. After that, what will you do? You have to respond fastly.
Then we will map the new intensity values for everything. However, change only for the pixel of interest.
Right. So which are the pixels that you are going to replace now? That's my question.
Only that one pixel around which everything is centered, that one which are mid star.
Right. That's right. So yes, whichever, let's say the center pixel has an intensity of 10, it is just through the histogram equalization, you would see where this 10 got mapped to 10. So if you remember R and S cap, you have it yesterday. So what is this going to? Let's say this is going to 0, assume that that's the least one you have, and maybe it is going to 0. In the new image, it is only that pixel you are replacing. Okay, so this way you are going to repeat this whole process for every pixel, ignoring of course the boundary things. That's you will deal with them separately. Is this clear? This is something every one of you is going to implement in a program. So the concept has to be very clear to you. Is it clear so far? Let's say you want to construct a histogram, right? So in this whole process, suppose I have a histogram of size m cross, yeah, or maybe m cross m. Okay, how many pixels are there? M square pixels are there. Now I'm using a window of w by w. So w square pixels, with w square pixels are the ones you have to access every time. So how many times overall by the end of your histogram equalization of all pixels and construct a new image, how many times you will be accessing the intensities? Or reconstructing your histogram also, you have to do the binning, right? How do you do, for example, how do you construct a histogram? Let's say you have 0 to 255 values are there. Each of them you will initialize that vector with 0. Now let's call this as a hist. So then what will you do? Assume that your indexing is starting with 0 for simplicity, 0 to 255. So hist of, for that I of x comma y which you complete there, that you will be plus plus, that array you will be incrementing it. So this histogram construction throughout this process, how many number of operations would be required in this way? How many order of what operations are required here? Order of, I have an m by m image, I have a w by w window that I keep at every pixel. So w square times I need to deal with this histogram, m
Sir,
square,
M square, W square.
right? Because at m square pixels, you need to repeat this, and at every pixel, in order to forget about the rest of the steps, just to construct an histogram, you need to make w square number of operations. Of course, that's not just querying, that's also additions and everything you have to do. Now, can you come up with a different way of implementation of this same algorithm such that this can be brought down? As I move from pixel to pixel, I am repeating this. Can you suggest me a better optimal way through which I could bring down this number of operations that would be required? Hope everybody is clear on why it is m square times w square, right? You have to do at each pixel w square. At each pixel location, you need to go through w square pixels, okay, in that window or neighborhood. Then you have to repeat it for m square times, because there are m square pixels. That's why it is m square times w square. Now, the question is, I want to bring down this complexity. Given that there is some overlap in the neighborhood, can you suggest me through in more clear terms on how you could bring down this complexity in construction of this histogram? Assume that this is my row. I did histogram calculation for this pixel. Now I am from here to here, I am moving. Okay. Now tell me, what in what way do you modify the histogram of that has been obtained for this pixel, such that with minimal calculations you will get the histogram for this? You tell me now. Even for simplification, if you want, I would give this also. Now you do not have any more excuses to not to answer this question. That's where a 3 by 3 window is what you are using. Okay, now you tell me how you compute the histogram, how you update the histogram of the previous one such that you will get the histogram for the new pixel.
I'm not sure, sir, but since
Hmm,
we are moving column by column,
right,
so the center column is common, sir. That is,
right.
the second column is common.
Is it only
So
the second column or something else is also common?
The third column.
Second column
second
and
third.
two columns are
Yes.
common.
Third column is also common.
So we just
Only
subtract.
correct. Very good. Very good. This
We
is
just
the one
we
which subtract. And what is the one you need to add now?
The fourth column.
That's all. See, this is not a very challenging question. That's all you have to do. As you are moving here, the same code you do now, whichever you have done earlier for these columns, there you do minus minus first, your earlier histogram.
We just remove those many number of pixels.
That's all. Removing that pixel means in the
3 pixels.
histogram, that value you reduce the count by 1, whichever you have been contributed by these pixels earlier to the histogram, you remove them and simply add them here. So
Yes.
you could notice here, this has, you should be also able to express it in terms of this computational complexity also. Now, can you tell me what would be the computational complexity with this implementation? Assuming I'm using a W by W window.
W into, sorry, 3 pixels. So W
Yeah,
into 1.
that is because it is a 3 by 3 window. Just think now generalizing that to 5 by 5 window or 10
Just
by 10 window.
Just W. Sir.
Yes, that's right. Of course, you are accessing 2W, but you will always drop the constants when you are saying about computational complexity. Good. So this is going to be order of M square times W. Okay. You could have moved in this direction also. Then what would happen? So earlier, I covered this whole row in this process. I am done with this row. I'll come down now. Okay. So let's say if I am doing that, then when I am coming down, of course, you could either do this row wise. Okay. You do the calculation, you finish it there. You can come down and do it. Otherwise, you just calculate one more. That's okay. Because only 2m times you would be doing it afresh. But there is no reason why you should do in this manner only. You could do in this manner also. If you are doing it this way, still it will be the same, assuming that it is. Now you would subtract from the histogram the contributions from the top row and add the bottom row. That's all you will be doing. So is this clear or any questions? Is it clear to everyone? At least say yes. If you are not earlier saying answers, I would like to hear more.
Yes, sir. Yes, sir.
More good. Then just to let you know, although you might not be implementing this, is that there are other ways people implement this histogram also. One way is the whole image, they would treat it to tiles, where for example, this is a tile. Each tile could be, let's say, something like 10 by 10, let's say. Okay. Then what they would do is they calculate the histogram for that, and thereby the mapping is found for each tile. Okay. And this is a zoomed version of your tile is this. And now for any pixel, so this is one tile. Okay. Another tile here, another tile here, another tile here. Again, for a time being, ignore those pixels which are there on the boundaries. Take anything in between. What will you do now for that is you would see how this mapping, it is like a linear interpolation. You look at all this four, you all know how a linear interpolation could be done. If this is A, if this is 1 minus A, you have here, you know, its value here is X, you know, here the value is Y. So of course, then you would do 1 minus A times X plus A times Y kind of stuff. Closer it is here, right? Then larger value A is small, so that is much closer to X. If A is large, that means it is close to Y. So that's why A is where A is in between 0 to 1, you take it. Okay. So in similar lines, you do here, this being a 2D image, you do a bilinear interpolation based on these 4 points within which it is there. And that's how you find the mapping. And here you do a histogram equalization only for those tiles, not for every pixel. Okay. And of course, there are different variants. If you look at the literature, there will be a lot of things. In the interest of time and the topics of our interest, we will not go in depth right now. For example, people will do without any overlapping windows, and there is some other thing that they will be doing it, but enough to know till this point. Okay, so hope this tiling based approach is clear. Right. And the last topic that I would cover you, that I would like to mention to you in histogram equalization is adaptive histogram equalization is same as local histogram equalization. You call it adaptive because it is locally varying. Okay, that you keep it in mind. Then there is something called as contrast limited adaptive histogram equalization. Consider there is in your image a region which is almost of constant value, except that there might be some noise here and there. This is pretty much expected. Say, for example, take the feed of my video itself. All the background you could expect to be of almost constant image. Maybe some noise could be added because of the resolution or some other thing. But then think of what would happen to it when you do a histogram equalization on that. Obviously, in a constant region, there could be something like this and a big peak there, right? And these noises which are there now will get amplified a lot. In order to avoid that, there is an approach where you put a cutoff here on your histogram, and whatever this value is there, now just think about it in terms of number of pixels instead of, or of course nothing wrong in thinking about the PDF also. That is okay. Let's say you don't want anything about 0.6. This 0.4 you would equally distribute to all the values here. So that means initially if it is like this, let's say I put a cutoff of 0.6 on the threshold, this would lift the base for your histogram for all the pixel intensity values. And of course, this being your cutoff, now still there is a small value. You repeat the whole process now. Maybe now this will lift your thing a little much there. So then you repeat it until it is within some threshold. Okay, let's say as long as it is less than point, let's say not 5. Okay, I'm taking 1, so 5 something like that you can take it. Okay, then you will stop, and it is after that you do histogram equalization, and then you find mapping, and then you go to your original histogram, and to those intensities you do the mapping. This is referred to as contrast limited histogram, contrast limited adaptive histogram equalization. Adaptive histogram because you would do it locally and you could mention here what is the window size. Contrast limited, let's say you could say here what could be the maximum threshold value that could be there. Let's say you don't want anything, something not more than 60% for any individual intensity. The CLAHE command will be there if I'm not wrong in MATLAB. If you are doing in Python, something similar to that is there. So even if you do not implement it, this concept should be there for you. This intuition for what contrast limited adaptive histogram equalization does and why it makes sense, that concept should be clear to you. I hope that is clear. Or any questions on that? I'm not going into the complete implementation details. I will not be asking you to implement this as it's an iterative process, not difficult to implement, but it's okay. I may at the most ask you to actually call some existing function and see how the image is. I won't be asking you more than that for this from the implementation point of view, but nevertheless, the concept should be clear to you. So here are some examples again of the Mars satellite of the Mars. Okay, so there also this is the original image if I am not wrong. Then they have used adaptive histogram equalization, that is local histogram equalization, and this is the one where they used contrast limited adaptive histogram, or same thing again. Tiling is what they used. Now instead of using the typical one, they have used 25 by 25 window around each pixel. or for each tile it is 25 by 25. I'm sure this might be of 1000 by 1000 or 1024 of similar nature might be the size of your image. And of course, it looks like you have a number of rows then columns. Don't exactly remember, but it's okay. That doesn't matter much. Then this is where there is a clip limit where it cannot go beyond 5% if you look at it. So, particular region is contrast limited. So that's what you are equally distributing. You don't want your histogram to get too much driven by this concept, but you are putting a limit of clip limit of 0.05 there. And it looks like this result is better than what you would be getting. So you could see that in fact, for example, the snow around this place is visible in this image, which otherwise is not visible in other images. So it seems it helped because it's a kind of a lot of constant region is there. So it seems it has helped. Another example before I wrap up this is this is the input image. Somebody like you guys have taken a photo of it and then you realize that there is a shadow there. You could see a shadow forming there, non-uniform intensities. And if you recollect, when in your histogram, when it doesn't have a 0, there is a gap here, and then there is a gap from L-1, what would happen then? Obviously, this would move here and this would be moving here. In other words, when you are somewhere in between the spectrum from 0 to L-1, your dark pixels will become much darker and your bright pixels will become much brighter. Okay, if you are applying a histogram equalization or even contrast stretching, if you are doing, you will see a similar effect. Well, that did not really help because this part has become completely dark. You see some shadow there. This part also has become darker. On the contrary, if you are using the localized histogram, this is the result that you would get. And obviously, that's far better than what you get there. Of course, you might have noticed here, you are applying it on a grayscale image. So this color is not there. Of course, if you want to retain color also, there are ways you could apply where you could do it. Let's say there are different possibilities you could do for each channel, combine it and see. But typically, maybe that's not your objective. You just want to finally send to your instructor of your course something which is better. So you could see there adaptive histogram equalization works well there. Okay, so with that, I'm going to wrap now. Histogram equalization, adaptive histogram equalization, contrast limited adaptive histogram equalization. And of course, the beginning we had all discussions about why a histogram and contrast different types of intensity transformations that you could do. Okay, I'm moving now to a new chapter within image processing. Now this is about filtering. So before I move on to filtering, are there any questions on this module so far on all these things? Do you have any queries, any thoughts to share? So what we are going to do now is to take a look at image enhancements using spatial filtering. Again, pay your full attention and please be with me, answer the questions interactively so that I can move a little bit faster. Let's consider an image here first. Let me draw a few pixels of that. Let me call, let's say this is each row is indexed by X and column is indexed by Y. These are my rows. Let's call this as my image. Please make a notes for yourself also. I'm not going to upload it again because if I have to upload, I need to write it more clearly, which will take some time. So please make a notes for yourself. Okay, I have something like this. Right. Now, what I want to do is assume that there is some noise here and there that got added to this image. How do you remove that noise? Or even let me call it as you want to smooth the image. Can you say a simple operation through which you can smooth the image?
Averaging.
Very good. That's all. So averaging. Yeah. So let's say I call the original image as I of x comma y. Okay. I do a perform a smoothing here. Let me call that image as g of x comma y. Say, let's say for doing this, what he is saying is, let's say I want to do a smoothing where in order to find out the new pixel intensity for this particular pixel, I consider a 3 by 3 window there. Assumption is all neighbors are having a similar one. I take an average of intensities of all pixels around this window, which is centered at our pixel of interest. And that average value, I replace it and that I call it as g of xy. Okay. Now, let me call this as let this w by w is a 3 by 3 window for me. Now, can you write the expression for g of xy in terms of I of xy given this? Tell me in terms of these are integers now as you are moving there. So give me an expression, express g of xy in terms of I of xy. How do you do the averaging? You tell me that. How many pixels you are considering here?
9.
9. So I would just average is 1 by 9. Now you tell me. Let's say the center pixel itself is f of x comma y. So I will write that. And now
I
I
of
would
x.
like to let's say consider. I think I have drawn one extra here. So I should have drawn this like this. I think okay. I think my drawing was bad, so this was in fact the green part. Okay, yeah, 3 by 3. Okay, so let's say what is this index of this one? How do I access that value which I put a dot now? I of f of, so I'm calling
F
it
of
I, right? I'll
X.
call it as I. Okay, I of, this is my vertical
Y of
axis
X
is
minus
x.
1 comma Y.
Y
I of
x comma y
x
minus
comma,
1.
right, I of x comma y minus 1. What about this? I of,
I of comma y plus 1.
very good. And then let's move on to this one here. What is this? I of
I of x plus 1 comma y.
x minus 1. Oh, because my x is down. I of x minus 1 comma y. Okay, anyway, I went there. Let me finish that row first. So x minus 1th row is that. Now you tell me. What is the new one I have kept there? I of x minus 1 comma. My x is
X
like
minus 1
this. My
comma
y is like
y
this.
minus 1.
So, right, y minus 1 plus I of x minus 1, same row, this one, let's say. Oh, sorry, this one. Oh, I forget about this. This one. Here, this top one is I of x minus 1 comma
Y
y
plus
plus
1.
1. Right. Now, similarly, let us write here. Let's come here. That would be I of x plus 1 comma y. Here, I of x plus 1 comma y minus 1. And here, I of x plus 1 comma y plus 1. Right. Well, now let us generalize it to any size of window w by w. Let us write that expression for this. So let's say, further just to, for a, typically you would consider a window of odd number, because then only you will get it centered, right? 2, for example, on the right, 2 on the left. So 2 plus 2, 4, middle one is 1. So then 5 by 5. Even if you take one here, one to the left, one to the right, one top, one down, then also it is like 1, 1, 2, middle one, 3. Okay. So since you are having a symmetric one, W is odd, and then so W by 2 when I say it, because these are the W by 2 I should go there. For example, when I have 3 by 2, 1.5 value, but again this would be like 1 here and 1 there. This 0.5 is or if I have, let's say 11, so 1, 3, 5, 7 you take, for example. Okay, then you have, how much is that? 3.5. That means 3 on one side, 3 on the other side, middle. So I should take there essentially the floor value. Okay. So W by 2, when I say it, I'm in fact taking the floor value of W by 2. That's the integer I'm considering it. Now, you give me the g of xy expression now in terms of a summation. Okay. For your easy follow up, let me put two summations there, one multiplication factor there, some I here. Let me use capital I, small I here, small j there. Now you tell me first, what is the multiplication factor I should keep here?
1 by
W by
9.
W window. W by 2 is what I would consider. Okay, W by 2, when I say it's a floor integer, right? Tell me, what is the multiplication factor?
1 by W square.
1 by
1 by
W
Right,
square.
right, 1 by W square. Okay, so let me also write here x plus I comma y plus j. Okay, now you tell me what is the I range that I should change, vary.
Sir, 1 to 9.
No, sir. I want it now for W, any value of W, which is odd. You tell me in terms of W now, the limits.
minus of W by 2, floor of W by 2 to plus W by 2 floor.
Right. Just for convenience, I'm dropping the floor. Otherwise, strictly, I should be keeping floor there. But let's put it that way. J is varying from minus W by 2 to W by 2. Very good. Look at, for example, the case which we have written there. There, my minus W by 2 means W equal to 3. My W by 2 is an integer 1. So minus 1 to plus 1. J is varying from minus 1 to plus 1. That means when I am varying from minus 1 to plus 1, there is minus 1, there is 0, and there is 1. Correct? So that will give you the expression above. And this is what a generalized expression for averaging, doing in averaging there. Clear so far, or any questions on what I have written there? If so, if it is clear, I'll go to the next step. We are going to build here brick by brick. You will finally come to the final expression. To keep things simple, I started with taking a simple 3 by 3 window, that too a simple averaging filter, but we will stick neither to the averaging filter nor to a simple 3 by 3 window. So we will be keep on generalizing step by step. So because of that, this has to be clear before we go forward. Any questions or doubts so far on the expression that I have written? Somebody
Yes, sir.
has. Okay, right, good. So let me now go to one more step there. See, when I want to average, I have a pixel there. Okay, and let's say I have an image like this, 3 by 3 window. Is it not, while I am getting a new value for that in my, this is my input image, I am writing it to Z, I might want to give how far is that neighbor. For example, whichever value is here, I give more weight to it while I am averaging. And next high, second level, more weight I will give to immediate neighbors, because even if you see its distance, these are somebody who are your neighbors who are in the diagonal. Okay, square root of 2. If you consider this as 1 and 1, both x and y are varying here only. Either x or y is varying. So the next final weight I would like to give here. That means, for example, what could be those weights here? I would give maximum weight of let's say 4 here. Then I'm just putting some values empirically here, okay, just to illustration. So then I give 2 there, 1 here, and now here what I did, I gave equal weight to in deciding what should be in the new image, the pixel at xy should have it. But now I am giving different weights here. So what I will do now, I sum up everything. Now the way I do it is 4 times I of xy plus 2 times I of 2 times, I am changing only 1, y minus 1 or I am doing x of y plus 1, or I'll be doing I'm changing in the x, so x minus 1y, or I would change it to x plus 1y. Okay, and only one weight here when I am changing both. Okay, I could write those 4 terms corresponding to these values then. Okay, I leave it to you to write that. Then how should I normalize it with which value to get the new value? What is the normalizing factor there?
1 by 16.
1 by
16, sir.
1 by. So it's simply the sum of all these things, right? So that will be 4 plus 2, 6, 6 plus 2, 8, 8 plus 2, 10, 10 plus 2, 12, 12 plus 4, 16. So I simply do 1 by 16. Okay, and there could be some reason which you would see some of the possibilities a little later, where you could want to keep these weights also general. So how could you achieve it from here? See, here I have simply considered equal weight for all the pixels. I don't want to do that. Then how can I achieve this? It's very simple. That of course this 1 by w's, this that can be achieved by writing my g of xy now as summations I varying from minus w by 2 to plus w by 2, j varying minus w by 2 to plus dw by 2, I of x plus I comma y plus j is anyway there. I am writing here h of I comma j. For example, for the example that I have given you above, this is by the way referred to as weighted averaging filter. Earlier it is simple averaging filter. This is a weighted averaging filter. For example, there for a 3 by 3 window, my this pay attention to where my I and J are here. They are at the center, not like the image there. This has to be clear. The center is here for an image. For your mask, whatever you are going to call now this h of I comma j, it is here. So my weights here would be simply this 4 2 2 2 2 1 1 1 1. With this h of I comma j, am I not achieving whatever I have written above?
Sir, one question, sir.
Yes, please.
Like, sir, suppose I'm just giving an example of an image, what I have actually thought. Like, each image will have some pixel value, sir.
Hmm.
Instead of fixed value, we are fixing this number 241.
Hmm.
And with this factor, we are multiplying to those pixel value, and then we are taking the averaging.
Correct. So this you refer to as a kernel here. You won't call it as an image. This is a kernel that will tell you to what weights should be given to your multiplication during this process. You could, of course, as you rightly said, you could think of it as an image also and multiplying it, but a better way is to call it as a kernel there.
Right, sir.
Sir,
Good.
we'll divide by 1 upon sigma hij also.
Very good. This is what I would absorb it into it. Very good. That I missed here. So if I have to write it, good that you mentioned, I missed that out. My weights now, I will keep it this way now. Very good point. Sorry that I missed earlier. There is some factor I should have written here for this when I do it. So everything here is the weights. I will absorb that multiplication factor also into this h of I comma j. Then is that fine?
Then it will be fine.
Right. Very good good that you pointed it out. Any other question or doubt here? This is the foundation for what we will be discussing later. So this concept has to be very, very clear to you. By the way, did you guys see such expression anywhere? Just look at it instead of the 2D. You just keep one indexing there and drop the other. And then what is that expression then? Can any of you comment that? What is that expression that I have written there?
Convolution,
Correlation.
correlation.
Right. This is not convolution here. This is correlation. Since you have mentioned this is an expression for correlation. So you are, in order to perform some type of operation on your input image, for the time being, we consider that as a smoothing. But in the upcoming classes, we will consider something else, finding out edges. You could do it by correlating your image with a kernel. Hope now you understand why I am calling this as a kernel. And that would perform the operation throughout your image. Since one of you had mentioned the term convolution also, can you give me now the expression for convolution? So let me call it with something else. Okay, h of x comma y. With convolution, I want to convolve it with a kernel. So then how do you write it? This is equal to minus w by 2 to plus w by 2. This is again same thing here. J is minus w by 2 to plus w by 2. Then you tell me what should be there inside. For this operation to be, now what it signifies I'm not talking about. I just want the expression for convolving the image I of x comma y with a mask or a kernel or a filter h of I comma j. Tell me how you do this. Give me the expression for it.
So we can just say have images the same, sir. X plus I plus, comma y plus j, and the mask, the kernel will become h of minus I minus j.
Very good.
Invert.
Very good. Very good. A flipped mask. So convolution and correlation are kind of, they have an equality, they have a duality there. If you flip the mask and correlate it, it is equivalent to convolving it the original mask. Or the other way around, you want to convolve with a particular mask. Okay, if you can do convolution with correlation function and correlation with convolution function by simply feeding it a flipped mask. But now you all know the properties of convolution. Based on that, is there any other way you could do this flipping operation thanks to the commutative property or other properties of it? So how else can I write that? Any other way to write that? Tell me another way of writing the same expression. What is another equivalent expression? I of
x minus I
mm,
comma y minus j into h of I comma j.
That's all. Either that will be equivalent ones. You all know that. I don't have to repeat that because you did it well in your signals and systems as well as your DSP course. These are very, very important operations. What we realized now is if you want to do any linear operation, in fact, of course, we are not rigorously shown that this is a linear operation, but you know that convolution is a linear operation. So that way you can justify that you could achieve either through correlation or through convolution by simply figuring out the appropriate kernel that can represent that particular operation that you want to do. Is that clear? Or any questions? So I would ask, you all know how to do a convolution in 1D, but you have here a 2D case. So let's say let me give 10, 20, 30, 40, 50, 60, 70, 80, 90. This is my h of I comma j. Of course, this is my I. Why I was very keen on mentioning where the I and j are. Otherwise, when you are performing this minus I and minus j, everything will go for a task. So that has to be very clear. So now tell me, how would you compute now this mask? For example, if you want to perform a convolution, let's say Okay, so hope it is clear by this time that you can do convolution with a mask in order to get a particular linear operation on an image to be performed. Okay, now assume that I have given you this h of I comma z. What is the convolution? This is your center. So typically you put a highlighted box around that. Now, how do you do the convolution of this? One way is you would look at, for example, the 10 is there here, minus I minus j. So this I equal to -1 here, let's correct, because this I is this way and j is this way, right? J equal to -1 here. For this, if you consider j is -1, and what about I? I is -1. So -1 to 1. So one flip would bring it here, and another axis will bring here. So this 10 will come there. This 20 will go a flip here, but a vertical flip will keep it there itself. So 20 will be here. This 30, one flip will bring it here. Another vertical flip will bring it here. So that would come here. So on and so forth. You can do it. Another easier way is, this being a linear operation, simple thing with little bit easier. Of course, it might vary. You might feel the other way around also. Is that first you do a horizontal flip. That means I would simply write here 10, 20, 30. This middle row, when I am doing with respect to the middle row, 40, 50, 60 will be here itself. Then this 70, 80, 90 would come here. Then I do a vertical flip. I should write F here. Vertical flip around this now, right? So that will give me 90, 60, 30 will come here. 80, 50, 20 would remain there. And here 70, 40, 10 would come there. So this will go here and this will go here. That's all. This is your h of minus I comma minus j. Think we have discussed enough things today. I will stop here. And in the upcoming class, so far I just used this smoothing, the two weighted average smoothing, and so far I have used just this weighted averaging filter, simple averaging filter. These are the two as excuses to explain you these things. In the coming classes, we would see more other types of filters also, particularly the gradients and other such things which you could compute using these masks or kernels, whichever you may call it. Okay, that's what we will see in the next class. I'll stop here.